doubt that it's a beautiful curve. It's a beautiful, we've been talking about it all term, right? We keep bringing up, oh, when you have bell-shaped data, 95% of the data is within 2 standard deviations. And it's gorgeous. We keep using that, and you've dutifully accepted the 95%, the 2/3, and this and that. You've been very, very good, studious students, and you believed every word I said. Nobody ever questioned, why the hell is it 95%? Because it always works? That's hardly proof. It doesn't explain why the sun rises. Why does the sun rise? Because it does every day. That loses the fact that the Earth rotates around many things, let alone the sun. I mean, we have to understand why these things are. So, let's start developing that. I'm going to sketch a bell curve. And we're going to see how this ties to this. Because it does. It is continuous. That's the big difference, is this is going to talk about continuous data, and this is going to talk about discrete data. But this right here, we're going to call this the normal distribution. Now, distribution, and then there. All right. There are other ones. Remember how the binomial was only one of many discrete distributions? There are other continuous distributions too, which we'll get to in 244 when we need to. We do not need to get into those right now. There's no need to get into those right now. We can talk about this one, because this is the perfect, this is, Carolyn, as you pointed out about 15 minutes ago, the perfect kind of bridge gap to 244, but it also helps us answer questions that happen in our lives without 244. Now, this is your beautiful standard normal curve. I'm going to place the number 0 right in the middle of it. The reason I'm doing that is because we are going to be talking about the standard normal distribution today. On Thursday, we're going to make it more general. We're going to make it more general. The general normal. Now I'm going to make a note to this general today. We're going to come back and talk about why we're going to ignore that until Thursday in about 15 minutes. I'm also going to slap some other numbers on the curve. There are zeros in the middle. I'm going to put a 1 out here, a 2 here, a 3 here, a -1 here, a -2 here, a -3 here. And because I'm getting tired of writing, I'm going to put some arrowheads here. I'm going to let them go off forever. What do you think that corresponds to?
Infinity.
Back here. Good! Negative and positive infinity. Excellent. A more specific question though, Lauren. Thank you for that answer. What over here do those numbers correspond to?
X.
Exactly correct. These numbers here correspond to the values of x here. Now I know they look different because there are negatives here or there aren't negatives here. I understand that, and that's a very, very good observation. Some of you are nodding like, yes, I saw that too. These are called z-scores. These numbers that are right here are called z-scores. Why are they called z-scores? I'll be damned if I know. I don't know why they're called z-scores. It's one of those historical artifacts that got handed down to us. They equate, though, to the x values over here. But they're way more powerful than that because they give us more information. For example, a z-score of 0 means you're at the highest point of the curve, which means a z-score of 0 is the what?
Best.
In what way?
I don't know. The highest.
It's the highest probability,
Yeah.
which means it's the...
Most likely.
Say it again, nice and loud.
Average.
It's the average. It's the average of the curve. It's also the median, it's also the mode, right? I mean, depending on however you want to look at it, it's all three of those I've talked about before. So in the standard normal distribution, the average is 0. Why? Because that's the way the curve is set up. If you draw a bell curve, your average is at the highest point. Your average is at the highest point. The highest point, if you make the highest point equal to 0, you're on your way to create what's called a standard normal curve. More about why we're setting it equal to 0 momentarily, because it's not usually 0, it's usually something else. I want to draw that connection too. What are these guys? -1, +1, 2, -2. Those are z-scores. What does the negative z-score imply? It's less than average, and a positive z-score implies that it's greater than average. Good. what else do you think? Hopefully I've drawn them somewhat correctly. What else are they?
Standard deviation.
They are. I drew it close enough, you guys saw that. They're the standard deviation measures, which means the standard deviation of this curve is equal to the number 1. Because when you go out 2 from average, you pick up 95%. When you go out 1, you pick up roughly, what is for 1? Roughly 2/3, good, good. When you go out 3, what do you get? Do you remember 3? We didn't talk much about 3. We'll come back to it. We'll come back to it. Don't worry about it. Don't worry about it. We'll come back to it. Technology will help us with that. Yeah. But, can you go out somewhere between 0 and 1? Can't you? Yes? Give me a number between 0 and 1. How about a half? How about 0.75? Can you go out down here somewhere? What? How about negative root 3? Oh, what a bastard. But you see that number exists on that curve, doesn't it? Where didn't it exist? Here. There's nothing between 0 and 1 on this distribution. If Max goes into the store to buy 4 birds, and he comes out with 4 birds, how many of those birds could be girls? In that box. In that box. 4, 3, 2, 1, or 0. In that box, you can't have 1.1 girls or 1.73 girls. In that box. But on this curve you can. You can have an IQ of 100.123456789. If the number divided by the number equals that, that's your IQ, right? You can have any value on this line. That's why you don't want to do this with that kind of data. You'll be writing these numbers forever. Hell no. No, you don't want to do that. My God, you don't want to do that. I'm going to take some of these out because it gets a little hard to look at. But that's the point, is you can get lots of numbers on this line and they go off forever. Technically, mathematically, they go off forever. They actually do pinch off, realistically speaking. For example, what's your lowest possible IQ?
0.
Technically, it's 0, right? Now, for IQ, I'm going to throw a couple orange numbers on this general curve just to show you how technically it does pinch off. So here's 100. Remember what the IQ standard deviation was?
15.
You guys nailed it. It was 15. Remember that? So that means 1 corresponds to 115, 15 points above average. 2 would therefore correspond to, 3 would correspond to, so you can see how rare an IQ score of 150 was, that little precocious 4-year-old kid, right? Now you see some limitations. What's negative 1? That's 85. I think that was used to be called an idiot. Anybody with an IQ score of 85? Between 85 and the next one, which would be 70, this is where I think it was moron kicked in. Ever call your friends a moron? Idiot? Imbecile? Guess where those phrases come from? IQ levels. When you said dumb earlier, Austin, you weren't too far from the 1950s and 60s definitions of low IQ. Imbecile, idiot, moron, these are all IQ terms. They've been handed down to us as derogatory terms now, but they used to come from these breakdowns on the standard normal curve. Down below 70 would be, I think, what did I say that was, imbecile? So anything below 55. Now, clearly, eventually, you're going to run out of space. 55 becomes 40, 40 becomes 25, 25 becomes 10, and then you can't go any lower than that. So there are realistic constraints to the general normal curve. But I want to deal with those, if it's okay with you guys, I want to deal with those on Thursday, if it's okay. I want to deal with the theory today and the practice on Thursday. I think that'll make more sense that way. So just pretend they go off forever, because numerically they do. Cool? Okay. Now, you guys have already figured out that, use a different color, use gray. You guys have already figured out that if I go -2 to 2, how much of the curve is there between -2 and 2? You know the answer to this already, right? So if I ask you guys, what is the percentage of the curve between -2, I'm going to put z equals -2 and z equals 2? You know the answer. And the answer is 95%. So we know the answer. Now I want you to show me why it's 95%. Where did 95% come from? What does 95% sound like? You guys have already correctly surmised that these guys down here correlate to these guys right here. So what does the 95% correlate to? 2 standard deviations, but mathematically, what part of this image does it correspond to? Thank you, Corbin, for that. It's perfect.
Majority of it.
Well, the majority would be right here.
Yeah.
And believe it or not, just so you know, FYI, don't memorize this. The height of this curve right there is about 0.4 or about 40%. Now, don't memorize that, but just to give you a scale of reference, this height of the curve is about 0.4. Please don't memorize that. That is not worth knowing. But it gives you an idea of scale. So if that's 0.4, where does the 0.95 come from? 95% is 0.95, yeah? Well, let me ask you a question. Assuming I drew this somewhat correctly, what's that?
What do you mean? 0.1.
Ish, right? Ish. This is obviously a smaller percentage than this. And this would be, assuming I drew it correctly, should be about the same. It should be exactly the same, actually. The 95% that represents the chunk of the curve within 2 standard deviations is the area of the curve that covers that. And you guys did this earlier with me in my hands, remember? When I went like this, and I went like this, and you guys said, stop! What you were doing was you were trapping 95% of the curve between my hands. So 95% of this curve. My question is, what are these points up here? What are those? Give you a hint. What are those? What haven't we talked about yet on this distribution today? They're the probabilities! They're actually the probabilities. We have to add up. You know how you add these up and you get 1? The summation of all the probabilities equals 1 on this? Always? That has to work over here too. The problem, of course, is how many probabilities are there on that curve? Define a lot with 1 word. Infinitely. That's 2 words. Infinitely many. Sorry, I need 2 words. Infinitely many. There are infinite of them. Infinite. That's the response. There are infinitely many of them. I'm going to use 2 words, David. Infinitely many of them. So in other words, in order to calculate the 95% for the 2 standard deviations, I first have to figure out, okay, what's that probability? What's that probability? These are all within 2 standard deviations, yes? What's that probability? Don't worry about that. It's not important. Well, it's important, but don't memorize it. What's that probability? What's that probability? What else do I have to include? What, give me a number that's in there that I have to include. I'll use the ones you guys already did. Half, 3/4, -√3. Give me another one. Be brave. -1/2. Give me another one. 1.5. Give me another one. -0.14. 0.0823-ish. So what's going to happen is we're going to have to shade every single number between -2 and 2 up to that line, right? So what we have to do is we have to, what's the next number from -2 to the right of -2? Trick question! Nice answer. -0.199999999 off to infinity, right? But you encountered this problem back in geometry class in high school. You don't remember doing it. How many times did you shade areas in geometry? What's the area of that triangle? We can shade it, and look, oh, if we double it, it's a rectangle. Cut it in half, it becomes a triangle. You were doing calculus right then. You didn't even realize it. What you were doing with that shading was, you said, okay, that's a rectangle, that's a rectangle, that's a rectangle, that's a rectangle, 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 and the more you shaded, the more area you picked up, right? And Sarah's like, that's what I was doing? Yes, that's exactly what you were doing! And if you shade all the way across, you pretend there's no gaps. And you stop at -2. So you can pretend there's no gaps because I have given you technology that does this for you automatically. And that doesn't have any gaps. You'll see soon. In 10 minutes, we're going to see how the technology works. What did I just shade? 95% of the curve. Now, if you want, again, if you want more mathematics on why it's 95%, that's where that page online comes in. It breaks it down for you. It shows you the rectangles. It shows you how to get the estimates. If you guys have taken calculus before, you've done this. If you haven't, I'm not going to make you do it. So if you want to know what's out there, Daniel's like, I don't want to say this crap. That's good. Good. Good for you. Here's some questions I'd rather have you answer. What percent of the curve starts at -2 and goes down to infinity? What percent of the curve is over here. Vote for 2.5%? Second? Third? Woo! A woo third! How can it be 2.5 if 95% is here? That means what are you guys assuming about this curve by doing this, by the way? You're assuming it's 100% and symmetric, both of which you're allowed to do. You probably didn't notice this, but when the 10-mark bill was up there on the screen, you might have noticed the curve was e to the x squared power. That makes symmetry from Math 111. I'll not say it again. 2.5%, 2.5% symmetric. Yes? So now we know that if somebody has an IQ score of 130, they are in the 97.5th percentile, aren't they? They have beaten out 97.5% of people. That's pretty slick. That's pretty slick. And we can take this further. We'll talk about things like human pregnancy on Thursday. We'll talk about things like Michael Phelps and Mark Spitz on Thursday and how this all ties to all those different kind of constructs. Good. Let's use that symmetry. Excuse me. I drank a lot of the pool yesterday doing butterfly. If I was to cut the curve directly in half, what percent is here? Oh, sorry. Let me define here better, Austin. Good. Austin answered a very good question. If I cut the curve in half, 50% of it is here. I meant just the red section. Thank you, brother Austin. I meant just this bad boy right here.
47.
I love his answer. 47.5, right? Half the 95. So half of -2 to 0 has to be half of the entire realm of 2 standard deviations. Is that believable? Now, Austin answered a much better question is, if I cut the curve in half, what's down here? Half. You just said it. Thank you. Beautiful, brother. Thank you very much. I appreciate that. So everybody fine with that? Actually, you just gave me an answer to another question. What could we call, because of what Austin just said, what could we call 0? Since it divides the lower half of the curve and the upper half of the curve. It's the average for sure. It's the median, isn't it? It's the median, isn't it? Which would be the second quartile of 50th percentile? Is that fair? I got a fun question for us. We know what percentile that is, right? We know what percentile -2 is, don't we? Well, we have the next step to it. -2 down to infinity is 2.5%. That means it's the 2.5th percentile. Hopefully that makes sense. It separates the lowest 2.5 from the upper 97.5. This is a throwback to a couple weeks ago. Which means this guy up here is what? Yes? What's that guy right there? What's that guy right there? You have to use a bit of old information that we haven't used in a bit in order to answer this. Emily, what are you thinking of?
2/3.
Here's 2/3? Where'd 2/3 come from now? She started, thank you. She started by going, I know rule, because you wouldn't let me forget back in the day, that how much data is there? One standard deviation, which is roughly 2/3, roughly 66.67. Rory, go ahead.
How does 5% represent like to infinity when 95% represents like percent?
Hold that thought, brother. Just hold that thought for a moment. That's a great. Here's a question. How the hell can 2 off to infinity represent only 2.5% when -2 to 2 represents 95%? Hold that thought. Give me a couple more minutes if you don't mind. That's a great mathematical question with a pretty slick mathematical answer. Thank you. Let me finish this one first though, if you don't mind. So, we know that's 2/3, right? Ish. So what's this right here? Just this piece of that. That's 1/3. I'm going to call that 33% if that's okay. Can I call that 33%? 33, this actually is tied to your question, Rory. This part right here, that's 33%, isn't it? What's here all the way down? 50%. What percentile is that?
83.
Isn't that the 83rd percent by definition? Isn't that cool? 33 plus the additional 50 is about 83%. We're ishing this. This is all ishing. It's off by a percentage or two. Rory, here's your question kind of being answered. Look at how much area is contained between that and that. That's what, 33% of the data. It's far less here. And if we were to go out to 3, which we'll get to with the technology, it's going to be even less. The reason so much of the data is contained here, brother, is because so much of the curve is right there. As you go off to infinity, this curve pinches down asymptotically on the horizontal. So in other words, it's not just the fact that you can look at the numbers here, just like when you run one var stats, you have to put in L1 comma L2. This is L2. That's L2 now. If you think of it discretely, you have to weight it with that. 1 is totally different than 2, because 1 is that frequent where 2 is only that frequent.
Okay.
You're not sitting with that. That's not sitting well with you yet.
I think what he means is
Go.
why is P 97.5 97% going this way, and then but it goes to infinity both ways.
Oh, it's only 2.5% going this way. It's 97.5% going this way. See, percentile, this is a big throwback. I probably did it too quickly. Percentile always measures the chunks that you're above. So 2 represents being larger than 97.5% of the data. Now the infinity part does throw us for a loop, right? I mean, how can, if there's infinitely many numbers this way and this way,
Go
ahead.
That 2.5% represents that 2.5% of the infinite.
it 2, 3, 4, 5, 6, 7, 10.
It's always going to be 2.5%.
Always.
On that.
Always. On this particular standard normal curve, which we can always get back to, yes.
Yeah. Okay.
Is that decent? Thursday, I know will answer it perfect.
It makes sense. I just.
More sense, I hope.
Yeah.
Now, Kayla, I'm worried about...
Oh no, yeah.
You buy it. Okay. If anybody... Questions, please. I love these questions. Rory, it's going to make even more sense when we actually put realistic numbers on it. But yeah, the idea is, what we're essentially doing right here is we're learning how to use a screwdriver. And on Thursday, we're actually going to build something with a screwdriver, if that makes sense. This is very nuts and boltsy. There's no units. There's nothing interesting on this curve except for the curve itself. So we're kind of looking through, oh look, it's got a little square X thing. I don't know what Philip said. Yeah,
As more data collects on the outliers, though, it becomes a higher percent.
but here's the deal. Think about Max and OMSI. As more data collect on the outliers, what happens here? We get a lot more data in the middle. It's just like watching that simulation for Chuck-a-Luck. And I remember how I would jump, whenever we'd see 3 5s, I'd jump. But I would jump like once every 30 seconds, and in the time I'm not jumping, what's happening to the rest of the distribution? It's building up proportionately.
Yeah, unfortunately.
Proportionally. For every 2.5 balls being added here, 97.5 are being added here, proportionally. Thank you, brother. Probability, averaging, long term. Good, very good questions, very good questions. Now, as you can probably see too, this is a pain in the ass. Because we already covered it 3 times. Ruined the markers. You know, unless you guys are carrying reusable, erasable markers. This is why I gave you a program called STANormal. You have a gift. Take your TIs out. We've used dist fill. We've used dist draw. The last program I want to show you how to use is how to get these numbers off of this curve using something called STANormal. So I want to take the last couple minutes of class and walk you through that, and then Thursday we'll put them to use. Zoom in on the screen.